Welcome everybody. Okay, another night of coding coming up. We have a few things we're gonna do, mostly just for organization and debugging. So I streamed last night, but unfortunately I forgot to share the screen, so took that one down. I reverted the code. I couldn't revert it all the way to what it was before. I just had to go off the video I made last night that I personally have, but it should be pretty close. So that's also a good reason for me to commit at the end of every stream. So if I forget to commit towards the end, please remind me in the YouTube chat. Alrighty, let's get started. And this time I will share my screen. And it's sharing. Let me pull up my stream quickly here. Okay, now I can see the chat. All right, and before we get started, let me adjust my monitor, which is really just a big TV. I'm gonna use my feet for this. Perfect. All right, so first things first, we're going to take off our lazy pants and we are going to make our 3x3 struct into a templated struct. So this will be the same struct we'll use for filters if we shift to 4x4 filters, 5x5s, 2x2s, who knows what we'll do. 1x1 they'll be fully connected. Well, we're going to do this. What else we have to do? We're going to take our neural network and we're gonna write it to a CSV file. That way we can pull it up in Excel and see what all of the values are. In order to do that, we have to use a floating point that's supported by the processor, because right now, as you can see here, we're using this type def neural net float, which is a CUDA type __ half. So we'll be taking our struct, copying it to the CPU, and then converting our floats, our half floats, into full floats, which my Intel processor supports, and there's an actual CUDA library to do that. And then we'll be able to use a CPU to write to the CSV. We can't write to the CSV from the GPU. Not these days anyways, maybe someday. So transfer to the CPU memory is required for that. Okay, so we will template this struct. Dim for dimension, the dimension we'll have for this struct. And then also we're going to template it so that we can take this struct and convert it to whatever type of float we want. So we'll just say type float, our type of float. We'll rename it now to just filter. Since we'll be able to see every time we instantiate it what the size is. And our size will be dim times dim. So we'll have its dim size of 3, and then we'll template this as well with our type name tfloat. So whichever type we're using, all of our floats will get assigned as that. And for 3 here, we will use the filter dim we've defined here. And now we have this horribly ugly struct name. Line things up. All right, we're well on our way. Now everywhere that we call this or define it in a function, we'll have to put the type in. Whoops. Neural net float. That's what we want here. And before we forget, let's go to our definitions here. And here. We only need it for these declarations and definitions. We don't need it elsewhere in the code. And we will also need it to define it here so the compiler knows. How big of a memory how much memory to set aside in our compiled code. All right, that should do it. Okay, another way to take off our lazy pants. I thought of this earlier. Our output dimension from our input, so our first layer output dimension, that is a function of our filter size. So let's move our filter above our output dim. Our output dim, here, I'll pull up our illustration here. It's going to be how many times our filter fits as we stride our filter within our block here. So this is a 3x3. It'll start here and fit all the way to here. So we can think of it as like we have this one block here in the middle, and it has one on each side. As we slide it over, it will be taking 2 off of it. So basically, however big the sides are from it. Also, if we were to do a 2x2 filter, the math works the same. We would be moving 1 total, so we'd have 27. So the math doesn't work the same, as in the numbers aren't the same. But the fact is that we're taking you subtract 1 from the 3, and then you divide it in half. That's how many we're subtracting total. Oh wait, no, that's a better way to explain that. The formula is we take our dimension here, and then we just subtract this value, and we just add 1 back. So if we use a convolution size of 1, then we have a weight assigned, just a single one that'll be applying over our whole input array. So it'd be the same, the output would be the same size, also a 28 by 28. So we'd have 28, just subtract the 1, and then add it back. And you can see that our formula here will still work. So let's do that. Need a parentheses. Input dim minus our filter dim plus 1. 26. And that's all we need to do for that. Also, we're just striding by 1. So if we wanted to, we could also, some neural networks do this, because this would make the next layer array even smaller. But you could start here, and you could scoot over 2. You could scoot over even 3, although you wouldn't want to just not have them overlap at all. But theoretically you could, and that would be your stride. So if you have any type of stride, then the next layer size would be even reduced even more. Okay, so first layer output dim is 26 now. All right, I'm just trying to think of anything else we might need before we start printing these out. I think we're good to go. So let's create a file for our printing function. By printing, I mean writing the file. So we go to our util folder, and it's, should we name this? File writer neuralnet.hpp. Except spelled correctly. So we'll be using some CUDA API calls in this, so we'll have a CU file for it. Okay, we'll include a header file. Let's spell this right again. F2 to rename. We have a new header file, so it's pragma unst. And this is just a comment to say that this is the file. This is our matching header file here. Oh, this didn't rename. There we go. Oh, still not finding it. Oh well. Okay, so in order to print this, like I said, we've got to convert from GPU to CPU style float struct. So we'll say this is a CPU function. We'll indicate that with host, which is optional, but it's just basically like a nice little hint to whoever else is reading this. Oh, we don't have to return anything. No, we won't return anything. So we can just name this neural net have to float. And we'll be taking in our neural network struct, so we'll have to include our file that references it, that defines it. Project headers. Since I can't find it, it'll find it. It's being a diva. So use our namespace and class type, and we'll use neural network float. Let's use a smart pointer for this. So we'll be taking our neural network data in, and then we'll be pumping it out, but this time as a normal float. And this is not caps. All right, because we need this definition of this type, we'll take this in from the, we'll include the header here. Even though it's included here in the header that gets included, I like to have any headers that are ever used in any file. It's nice to have them on top, just as a little preview of for any developers, so they know what's coming up later. All right, let's get implemented. All right, let's split screen this so we can look at our neural network. The definition easier. There we go. So this is pretty straightforward. We're just taking our, our out struct and setting it equal to our in struct. But also converting it. So the way we do that, we have to include an NVIDIA header, which is the same one where the halves are defined. We just include this header, CUDA fp16.h, and we find a half to float function. Here it is. So it's coming in as a half. We'll convert it to a full float. All right, so we do it for all channels for our filter. Oh, there's and we have to do it for our weights. So we use the second loop for that J. And that'll of course be our first layer filter size. So this isn't running our network. This is just something we're doing for debugging. It doesn't have to be that efficient. So no need to over optimize it. Just a waste of time. So then we'll set our outputs, and these are all of size output size. Don't need these tabs in here. And our activation outputs. All right, I don't think there's any exceptions that can be thrown. Yeah, there's no exception. I doubt half to flow can throw an exception. So we're good to go. Let's not put this in our file writing though. We'll put this in our neural network file. And we can combine these again. Really, we should only be doing this. It's a half, since we're using half to float. We might use different types later. If I get a 40 series, then we can use 8-bit floats. All right, let's get started on our function here. So we'll use namespace util. We'll have a void type for this. Let's name it write to CSV. Neural net. CUDA. With CUDA, we won't use unique pointers. So for this one, we'll just pass in a raw pointer. They'll all be matching. Get our namespace in here. So this will be a neural network that's in our GPU. So first thing we're gonna do is we have to mem copy it. Actually, first thing we need to do is we need to create a CPU version of the half float version of the struct, and then a CPU version of the full float. So I'll have to use memory for this. The memory header file. To use our smart pointers. And we'll just start this with an H for half. Oh, we'll spell that. So we'll CUDA mem copying. First is our destination. Oh, we've got to allocate this. Next is our source pointer. I think this might get passed by reference. That should be fine. We need the size of our struct. And now it's just telling CUDA what kind of transfer it is, which is device to host. So I use our new keyword, and luckily that way it'll auto delete when this goes out of scope, which is good because we're going to be opening files and well, yeah, opening files, so that can always cause an exception. So I want to make sure our delete gets called. Now what we want is a new variable with our full float. Here we'll make a neural network float. And then if we change the type def of our neural network float, then this won't compile. Or I mean, when we call it into our function, it won't compile. All right, stream's looking good. Well, we've already got this namespace on this function, so we'll just call it have to float. Or we'll change the name of our function to have to float. Great, so we made our half neural network. Oh, that was changed. We allocated our half neural network, then we copied over from the GPU memory the data into it. Now we've created a new blank full precision neural network, and we've copied to it. Now to do this, I always like when I output a file, I like to prepend it with a date, in reverse order, starting with year, month, so it all just sorts when I sort it by name. So the time is in standard lib, our time functionality. We'll also be putting some statements. We need IO stream. To write our file, we need fstream. Also, just to make our string generation a lot easier, we'll use sstream for string stream. Say that 10 times fast. What else are we gonna need? That might do it. All right, so first let's make our file name. First we'll get the time. See, I have an example of this in a project I've done before. I've saved CSV before, but kind of for different reasons and in a different way. All right, let's make sure this is right because this is an old file. First off, I'll switch to my most recent naming convention to keep our project consistent. I like to just name variables with snake case. I wonder why it's not default renaming all of these. Can I check all? Oh yeah, I can up here. I don't want to say parameters because we're also saving the values that'll be in our neurons outwards. So information, which isn't considered a parameter. File name stream. All right, we got some cross-platform support already. And this is saving to a folder called saves, which I have here. Let's add it to the git ignore. Because these are going to be huge text files. We don't want that clogging up our repo. So just say we'll prefix it MNIST neural network. And I don't want these spaces between them anymore. Just between the day and the time. So we'll blank these out. Yeah, so here's how we get the year. We're also zero padding it. We'll zero pad the month, day, time, and all that. But so we get the year here, month, day, hour, minute, seconds. So I wonder how come we didn't. Oh, I think because I'm wondering why we didn't zero pad the day. I think with when you're using streams, the set fill with zeros is like what I would call sticky, meaning that all arguments afterwards will have this. I think even if we did another stream later in the file after this, it'll still apply. But with set width, that'll only, you have to call that before each value that you put into your stream. It's kind of weird that it's like that. All right, we'll rename this CSV file. Ooh, no, we don't want to change all these. Glad they asked. Just this one. Okay, before we forget, we will check if it's open or not. So if it's not open, that means something went wrong. So either we're overwriting an existing name, which won't happen, or even that wouldn't error it out. If there's an existing name and it's being used by another process, this won't happen, but it's good to have this. Or maybe if our saves folder isn't there. Yeah, when you guys check this out, there won't be a saves directory. How can we fix that? Is there a way like we can keep the saves folder but just nothing that's in it? I guess what am I gonna do? Should I just commit it with an empty saves here? And then put this in the git ignore so that it. so that it won't save anything that's in it. I'll just make a note of that. Since we're right in the heat of it all. This lights up green because of this to-do tree. And now you'll see it's here, which is really convenient. There's a few what they call tags that there can be. You can add tags as well. Do Control-Shift-P to do. So you open up your settings, type to do, and extension name to do tree if you have it installed. You can add tags, remove tags, filters. It's really cool. This reminds me too, I thought in our neural network, I know a way to optimize this. We'll be putting this in a function too. What we can do here is instead of looping through this, over and over again, we can, because these are independent data, arithmetic, we're doing arithmetic with independent data, so it doesn't depend on each other. We can just do this like 8 or 9 times, each time with like a slightly different index, and it'll do that a lot faster than having to go through a loop again. So we'll loop unroll it, which we can do manually. We can also hint at it with pragma unroll, but that's not guaranteed to happen. So this might auto optimize, but we don't know. We can check the pizzazz files. And also our CUBin files that, since we are specifically targeting an architecture, we'll be getting a CUBin file out. At some point in the compilation process, we might have to put a flag in to keep our CUBin file, but it has all the instructions that the GPU will be running, and we can look and disassemble it and then look at the mnemonic version of the machine instructions and see what exactly is happening and if we need to optimize this or not. And also we need to make our much better summation, since we're having that precision error because we're adding 192 half floats together. So at the time it gets to the last, who knows, like 30 or 40 half floats it's adding in, they're so small when they add into the large number, they're just, nothing's happening. It's just rounding them off into 0. So you have to come up with a better formula for that. And we'll have to optimize it too. Okay, so back to the code. Back to this part of the code. So if it's not open, that means something went wrong. Could not open file. And luckily we already have our file name here. Put in our end line. So we'll just print this error message and we'll return out of the function. We don't want to throw an exception or anything, because if we do this a lot, like we might train the network and save the network along certain epochs. It'd be kind of cool to go back and look at them, but if it can't save it just for one time, we don't want to stop the whole training process. And in the end, we will close our file. After we're done converting our half to float, we don't need this pointer anymore, so we just reset it and that calls its destructor. It'll delete it. So I like to put these lines in just as a note to whoever else looks at this that this is no longer needed anywhere. All right, so we're going to be printing this out to a CSV file. So we want our first line to label all of the blocks that we'll have. So our first will be input data. And we'll have a comma after it. So we'll have a block that's 28 wide. We'll have our label here. So we need to go over 28. Then we'll have a gap of some sort, which let's predefine. Let's see. We'll just name it array gap. So we'll have, for now, we'll just have 3 cells between our input data, and then the next thing we'll have is our filter weights. So we'll have a gap of 3 there. So just put in a bunch of commas in per blank cells. That's how a CSV works. I'll show you how CSV works. So we just have a CSVs are really commonly used all the time, so it's even an option. We can save it in code as a CSV. So CSV example.csv. You just have whatever text, and then you can open it in programs like Excel or OpenOffice. Actually, I have a CSV reader. There's an extension where you can do it in VS Code. Not surprising, huh? So we can just open this up, and it'll open it up as a spreadsheet. So it looks like by default it opens in Excel. See our spreadsheet here? Look familiar? All right, we don't need that anymore. Oh, and you always have to, it always prompts you to save CSVs when you're done. It's kind of annoying. Okay, so we're gonna put a bunch of commas in. The number of commas we'll have in will be input dim plus the gap that we'll have. I think this is gonna look so messy, but it'll work. Actually, before let's just make a stream where we populate all of this, and then we'll just write it to the file in one chunk. I've actually done this before, and it's faster to just write a huge string to CSV than it is to just like shoot a million commas into your open file. So yeah, we'll just have a string stream. CSV file contents. So we don't even have to open the file yet. So what we'll do here is we'll just stream in what we have. And we get the string out of the string stream. We get the string out of the string stream like this with the str. All right, so let's go here. Maybe this should be in its own function. I don't know, it's pretty linear. Let's just leave it. No need to abstract it. It's all linear. It's, you know, it's barely gonna get indented that much. Okay, so after we have our input data, we'll have our first layer filters. So the size of this will just be our first layer filter dim. Plus our array gap, and then we'll subtract 1. All right, next we'll have our raw output data. So this will be 26 wide. we need that output dim. We will have batch normalization. We don't have that now. But we'll keep this generic activated output data. I don't even know if I want to do batch normalization. All that does is, like, if all your points are clustered together, all your weights, then they have a small standard deviation. You take all the data, you subtract the mean, and then you divide it by the standard deviation, which basically means that if all of your output data is clustered closely together, then it spreads it out more. And if it's all spread out, then it shrinks it down more. It must be really useful because they use it, in industry and academia a lot. But let's try it without it first. Also, it's not really that efficient. It's not too bad. We'll try it without it a little bit. And then we'll do a comparison. We can do the same thing like how we Oh, that's right. I did the activation stuff last night. I think. But we can turn on and off batch normalization pretty easily with some CMake flags. Activate output data. Yeah, that's all we'll need. Okay, and then we'll print the data out. But first, we haven't compiled it in a little while, so let's try that. Take our define out of the namespace. Let's get a pointless. All right, so we'll populate our network, then we'll run our network, and now we will write it namespace util. Get to the path to the header. There we go, and then we need to take our implementation file and add it to our CMake. And we'll compile this whether we for both projects, so we won't have it in this MNIST branch. Which we'll kind of have to change it because we'll be using different defines. Which is fine. We might have to block all of this out if we're not building for MNIST. And then we'll have a separate file with all of this again, but with our super huge neural network. And then not block it out if we're using that. I'll have to make some more changes, but we're getting ahead of ourselves. So we're writing to CSV file our neural network. We just pass in the raw pointer, and we're good to go. Test it out. Okay, here's an issue. Our build failed. Saw a little splash of blood that came up on the stream. These reds. and it still ran the file, so we don't want to run our build if it fails. So the way you can do that in Windows is if you use a double ampersand in your batch file, then this command will only execute if this one is successful. Let's go ahead and change our we'll change our other batch files while we're here. And C makes fine. Also, let's get rid of these output indexes. The CSV file will be really helpful for debugging. It'll tell us if it'll tell us if we don't have our array indexing on point. Okay, it's a problem with our unique pointers. Oh, with our, and then for our streaming, we don't have our IO manip. Library included, so IO manip. Now, what are these unique pointers problems? Say no instance of constructor. Oh, we don't need new pointer here. That's right. Okay, we're just creating a raw pointer here that gets fed into a unique pointer. I think that's our issue. Some kind of error, unique pointer, function, something, default delete. Great error message. Standard unique pointer in, out. Oh yeah, we have to. When we call it into a function, it copies in there. We can't copy unique pointers. Okay. Here's a little secret. We don't use unique pointers that much in embedded C++. That's my background. I know, it's our dirty little secret. With embedded C++, it's basically just like C with namespaces and constructors. But they are a good idea. So would we be able to just pass them in by reference, I wonder? I'm gonna guess no. Let's rename this to convert. It's more specific. Expected an expression. That usually means semicolon problem. Well, it looks like it does let us pass them in by reference. So line 62, this is just a for loop. Size ti. Oh, whoops. Happens to the best. Put a semicolon on my define, which messed up the for loop. All right. MNIST neural network. Year, month, day. Yep, hour, minute, second. Sweet. How do I open this with my CSV viewer? Make sure I have my CSV viewer. Sweet. Okay, this starts with a 1. This doesn't start with 0 in this editor, so we have 1. We'll want our next tag, our next text to be at, it's like 28. At 32, I think. Is that 33? Because it'll end here at 28, then we want a 3 gap. Okay, yeah, so we do want a 32. And the first layer filter will be 3 wide here and then 3 gap. So it's because I didn't subtract 1 to this for loop. All right, cool. Now let's print the data. So we'll have a for loop for our rows. The amount of rows we want is going to depend on what our largest data, what our largest array in our neural network looks like. So for this, we'll use our algorithm library, and we're going to use stud max. So the height of our first box is our input data, so that's just going to be our input dim. So we're going to generate an array of integers, and then we're going to get the max is going to return to us the largest of all these integers that we put in. So we can just use our defines for this. So we'll say int max dim equals, of course. I'm sure this is highly templated. Well, these are all size t, so we'll just make this a size t. It's a little bit faster to use ints in for loops because signed integers, when they overflow, they're undefined. So there doesn't have to be any extra instructions telling the CPU to watch out for an overflow. If you have an unsigned int, then when it overflows, it's defined behavior. It has to wrap around and go to the lowest negative number that there is and go up from there. But these are all predefined. These are all integers. It's going to know at compile time what these are. But if the compiler doesn't know how many times it's going to loop ahead of time, it's better to use int. But we don't have to optimize this, so we'll just use the standard. Okay, so we want the max dim, input dim. So our filter, how many rows our filter data is going to be filter first layer filter dim +1 because we want a gap between them, and we'll just use 1. We won't use the array gap because this will be vertical spacing. Times channel amount times first layer channel amount. Now our next integer will be our output, our first layer output size, or dimension. And that's it. We can subtract 1 from this because we don't need a gap at the very bottom. All right, so we are going to be doing our rows. We'll have the outside loop be our row. So instead of using I, we'll name it because this might get pretty tricky. And the number of columns we'll want, it's going to be similar to this. Except we won't be subtracting 1 because our commas are here. I'll just make a variable here to calculate the size of our column so we don't have a super ugly for loop definition. So for our columns, we'll be looping in the number of columns we'll have is our input size plus our array gap plus our first layer filter dimension plus the array gap, then our output, which is for our raw output, and then we'll have another set of columns for our activated data. So we'll say and then we'll rename these i's to column for our column index. Okay, so if our column is less than our input dimension, that means we're printing up all of these we're printing up the data from our input array. So we'll need to know what our row is. So say if row is less than input dim, because it's a square, we'll put our data in. So we have our full neural network, input data, it will be our input dim times our row, because as we go through the rows we'll be reaching further and further into our array. So every time we jump down one row, we'll be going 28 more into the array. Because 28 is our input dim. So our input dim times row times plus our column. And that'll be the data we're putting in. So we'll stream that into our file contents. And we'll stream in a comma. Now otherwise though, if we're below where our block of data is, then we'll just be putting in a bunch of commas, just blank space. All right, so that's just for our input array. Actually, we're getting there. We got the filters and then the raw and the activated. So let's look at our filters. So here we can do an else if let's see here. Actually, we'll be putting in our array gap here. I'll just name this data gap. I'll just say print because we're doing text. Oh, didn't like that. So if it's less than here, then we're just printing commas. We'll always print commas here. So because we're using else ifs, we're catching anything that would already be in one of the previous printing loops that we're doing. So here's our filters. Data array plus data array gap plus first layer filtered in. We'll pretend we're starting at row 0 just to make it easier, even though we have a row above us. Oh, you know what? After we're done with our activated output data gap, or activated output data label, we can just go to the next slide. And we don't even need this loop. All right, for this one, we'll do if row is less than the size we're gonna have here. We might print so we're gonna have that one data gap. So we'll say if row does not equal 0, and row mod first layer filtered in +1 equals 0. Then we're just putting it in a comma. So if we're on our gap, we're just putting in a comma. Oh, this part's gonna be tricky. Otherwise, oh, we're even gonna have to look at how we have our struct structured. Because there's 32 separate channels for this. Okay, so the weights are all together. We're gonna make some indexing variables for this that the compiler can optimize later. So we'll say our int channel index. So the channel we're on is going to be our row divided by our first layer filtered in +1. So as we go down the rows, first 4 rows, that'll be channel 0. Next 4 rows, that'll be channel 1. Next 4 rows, channel 2. So this will give us that. Now we'll say our weight index we'll split these up. We'll do weight index x is just going to be our column minus all this stuff, or just these two. Actually, yeah, that'll just be our x index there. Int weight index y is going to be our row modulus this, our filter dimension, but not +1. There will be a +1 here. I need to be consistent with where I put my spaces around my parentheses. If I put them after or not. Let me know in the comments what looks cleaner to you. Is this more readable with the closely hugging, very protective parentheses, the warm and loving ones, or the more less helicopter parenting parentheses? So our weight index ultimately will just be our weight index y times our filtered in. This is where we leave off the +1. Plus our times our weight index y plus our weight index x. So we'll be outputting our first layer filter, channel index, and then our weight index. So let me just think about this again. Nope, that was a close one. Oh, you guys can't see that. My face is in the way. I'll move it to the left side of the screen. And then we need our commas in. All right, now it's time for our raw output data. I'll do the last case here too, so we can actually, we'll debug this right now. After I do this, after I print out the raw output data. Raw output data, we will never we just print one block. It's almost like I should use go-tos for this with all this. All the same line of code everywhere. But nah. Okay, we need that same else statement here. No. Well, I'm just assuming here. Oh, this is a big statement. I'm just assuming here that our filters will be our largest row, which isn't necessarily true. Or it might not be true in the future. So I'm saying if row's not 0 and it's not this. Yeah, because later we'll have like a filters with a whole bunch of channels. So I'll put parentheses around all of these and statements. Oh, here we'll have an or. Or row is, so if our row goes past where our last filters are, where like our entire stack of filters is, if it goes past that, then we'll print this. So actually I'll take these parentheses off here. So in every case, if we're below where our last filter row is, then we'll just print a bunch of commas. So if row is greater than first layer filter dim plus 1, because we have our gap, times channel, our first layer channel amount. And then we subtract 1 because we don't need a gap on the very bottom, but right below our filter. So printing our output data, this one will be simpler. All right, for let's set our first layer output dim with our row, then we'll print our data. From our raw output, let's get an index in here. So our column is like our X index. So we just subtract out all of this in parentheses. And with all the letters in it. So that's like our X, and then next we need our Y, which will just be our row times our first layer output dim, similar to above. All right, it's good enough for a test. We still need to do our activated data, which isn't done in our neural network yet. So we'll skip that for now. Let me make sure I'm using dims everywhere, not size. Okay. All right, let's try it out. Error. Hope I named these wrong. It's no autocomplete's not doing too hot. Oh, actually, I was gonna name these data print gap. All right, now we know we got all of them because we replaced them to 1 and back. Okay, so we're taking in this float. Oh, here, I didn't put my weight array in as whatever type name we're passing in. I don't know if you could see if my face was in the way, but here I still had neural net float, but we want it to be whatever float we pass in when we define the filter. Okay. All right, let's check it out. So here's the last one we wrote. Open File Explorer and Excel. Oh, didn't work. So this should just be a big block of 1s. Then all of these should be 0.1. We should have gaps down here. Oh, it went away. Oh, it didn't. Oh, okay. I just don't have a new line in. Phew, that'll be easy. Oh, I do have these activations here. Able to be used or not. I don't know if I showed that code on stream or not, because I had that incident. Oh no, this is just the wrong project. That's why. That's my other project I do to kind of work ahead a little bit sometimes. All right, yeah. So at the end of each of these, after we iterate through the columns, we will add a new line. Easy. Let's try that again. Here we go. Oh yeah. It's almost working. Oh, see these texts for these labels are too long. It messes up when we auto correct, or when we auto size our columns. Okay, so we have a problem here with the first layer filters. Yeah, we're missing this row at the bottom too. Let's see, so this starts at 2. Oh yeah, we have a problem here. Pretty close. Alright, let's fix it. Whoa, colorful. So we're iterating through the columns. Why would it ever keep printing our first layer filtered ins? Oh, I think I see a problem. Oh no. So we're printing out commas if our row is less than our if our printing out commas if our row is less than our first layer filtered in +1 times our channel amount -1. That's good. Oh wait, no, we're only going into this loop in this case. But I have that, I added this in here though. Oh, so I can just take this if statement off. Make it cleaner. All right, let's try that again. This is the one we just did, 23. Didn't fix anything. We want to just print 3 commas, 0, 1, 0, 1, 2, 3. Oh, I see an issue. So our problem is we're using 4 here, but so 4 to skip a line. So we'll have 0, 1, 2. So if the row is divisible and the row starts at the second row for a loop. So if a row is divisible by 4, then it will skip it. So here we have 0, 1, 2. We would want 3 to be skipped. Then here's 4, 5, 6, 7, 8 gets skipped. Okay, so we can just add 1. So we can just say if row I think +1. Let's try that. All right, that fixed that problem. I want to make sure these are all aligned properly too, so let's change our input data so that it's increasing, and then these numbers should all be increasing as well. So when we populate it, that will make it a function of our index. So each of our all of our input data will be a function of our index. We'll multiply it by 1/100. And I gotta pee. Alright, let's see what that gets us. Okay, yeah, so this is increasing as we go to the right and we go down. Let's see, how big is this? 27 to 220. So this is the right height. Why don't I see these repeat? Oh, these here are just repeats of over here. Okay. Good test we did. Looks like we're just missing our gap. Yep, data gap filters. And we need another data gap. Okay, that should fix it. Hooray! Okay, these should be going up by a fixed amount. So we'll just do this equals this minus this. And well, they're not going up by a fixed amount. Oh, well, these are on the edge. That shouldn't make a difference. I would think these would be going up by a fixed amount. Let's see if these are. These are not either. Let's see. Let's we do equals. We'll just do our calculations in Excel here. Our convolution one. So this should just be this times this, or this plus this, plus this. And then Just multiply by 0.1 because all of these convolutions are the same. 0.269. So that should be our output here, and it is not. So actually, we should be able to just drag and drop this to get the answers. Oh, these aren't going up by a consistent amount, but that's fine. It's just our loss of precision. The numbers are somewhat close. Let's check our differences between rows. Yeah, these are roughly equivalent. This is just, so these are correct, which makes sense because it's a pretty straightforward indexing in our neural network. These are not correct, so I don't know if we're reading these incorrectly or if it's our neural network. So I don't know if it's our CSV conversion or our neural network architecture that's wrong. Oh, you know what? We should. This needs to be fixed. We were multiplying by this filter, but it was moving around as we. The number it was multiplying over here was moving around as we were dragging it through Excel. Okay, so yeah, this looks better. It still doesn't match our raw output. So we need to go down 26. So if we start at 33, we should end at 58. Oh yeah, so these numbers then should match up here, which they're not doing. Oh, but I'm also adding these together 32 times. Forgot about that. Oh, there we go. All right, these are roughly equivalent. 217. Okay, cool. Sweet, yeah. See how this is helpful for debugging? Now we know our architecture is working correctly. We still do have that loss of precision for multiplying large numbers. Although, this 217 down here is pretty close to this one. Sweet. All right, and I'm gonna relabel our outputs, our labels here. Input. We'll know these are filters. Okay. All right, now let's just set our activated, but before that, we actually have the computer activated. So we'll do that in our neural network run. Actually, I'll do that another day. Getting sleepy and hungry. But yeah, so far, making some progress. Oh, and I'll git commit this time. Maybe I'll even push it. Oh yeah. Then when I select it all, I can auto fit it. These labels aren't messing with it anymore. Sweet. All right, let's make sure our save files aren't in there. They're not. That's good. And also I'll try to I'll commit it with the saves folder, so I'll just delete all these. And then I'll do another commit again while ignoring the saves folder, so that at least it's in the repo this time. There's got to be a better way to do it, so I'll look that up. Git add all, git commit, message, added filter templating. Well, that's less important. We'll start with the important thing. Headed right a neural network to CSV file. So my friend at work was telling me that there's actually tools you can use to like help visualize your neural networks, which is really cool. But we kind of have to do this anyways to use those tools, because instead of writing it to a CSV, we would write it as binary. So we have to get all our data organized, which is what this is helping us do. And so we'll have to write it whatever binary format is supported by these tools. The CSVs don't really cut it because it comes in as text, and you lose the precision on it. All right, git commit, and then change the git ignore to not have the saves. Make sure it sees it. Yep, git. Add all, git commit, message. Let's see what our status is now. Yep, okay, it's not bringing up the fact we have a saves folder. That's good. So git commit message. Added saves folder to git ignore. All right, now it's on GitHub, so you guys can pull this or clone it to your own computer and compile and run it and take a look at the neural network. I haven't tried compiling it in Linux yet. We can do that pretty soon. I've had issues with different distros and stuff before. I'm just gonna check if it compiles on the Jetson and on a Ubuntu 2004. You might have to set like your CUDA toolkit directory or your MVCC paths, things like that. Which if you have problems with, you can ask me. For now, since my audience is small, I just started. Now's a good opportunity to ask me questions. All right, and I still don't have any patrons on Patreon. Any donations are really appreciated. That can help me will help me develop on this project. So spend more time on it. Maybe even get some cool equipment. But anyways, thanks for watching, guys, and happy coding.